Greetings and welcome. In this session today we are going to see or solve a numerical on the simple air cooling system of aircraft refrigeration system. In last session we have seen construction and working and analysis of simple air cooling system using aircraft refrigeration system. So here is a statement of the numerical. We can read. The data is given, accordingly we will enlist the values. The simple air refrigeration system is used for aircraft cooling to take a load of 20 TR. So here 20 TR is a load, that is a cooling load given. The ambient pressure and temperature of air means these are the condition of air entering to the aeroplane ramming. Before ramming, that is a point number 1. So pressure P1 and temperature T1, that conditions are given here. 0.8 bar is the pressure, 20 degrees Celsius temperature. The pressure of air is increased to 0.9 bar due to isentropic ramming action. Means here after ramming the pressure is given. The air is further compressed in a compressor to 3.6 bar. Means after compression, this is the pressure value given. And then cooled in a heat exchanger to 60 degrees Celsius, means this is the temperature after air cooler given. Finally the air is passed through the cooling turbine and then it is supplied to the cabin at 1 bar. This is a condition of air at a cabin finally when the air is reaching, that is 1 bar. The air leaves the cabin at a temperature of 22 degrees Celsius. This is the cabin temperature, maintained temperature is given. Assuming that isentropic efficiency of compressor and turbine as 80%, 75%, and these are the values, constant Cp, specific heat of air value is given, adiabatic index is given. We have to calculate in this example mass of air circulated through the system, power of the system, and COP is coefficient of the system. So let us calculate. So for that purpose now, here first of all we have already enlisted the data. Let us do the calculation wherever is required in the required format. Cooling load here we need in a kilowatt, so we have to calculate that with multiplication factor, that is 3.517 kilowatt conversion. So that comes 70.34 kilowatt. 20 TR is the capacity of the system. Ambient temperature T1 in degrees Celsius, we need it in absolute, means we have to add it by 273, then we will get this 293 Kelvin. Pressure value P1 already we have discussed about it. This one temperature we have to convert in a Kelvin, so that comes about 333 Kelvin, and this last one, cabin temperature absolute value, that comes 295 Kelvin. Efficiency for the calculation we have to take 80%, means 80 divided by 100, 0.8. Similarly this, and further these gamma and Cp we will use in the calculation. Now for this calculation, first of all we need to have a TS diagram. So let us see first of all TS diagram. So here this is a TS diagram which is used for the analysis purpose. Here we can see this P1 ambient pressure is given 0.8 bar. 1 to 2 process is a ramming process, and as it is mentioned in the numerical, isentropic ramming process. That is why here we take this 1 to 2 line as a vertical straight line. After ramming 0.9 bar pressure, then compression process by two ways. One is ideal process 2 3 dash and actual process 2 3. At the end of compressor, the pressure is given 3.6 bar. Then 3 to 4, this is a heat exchanger cooling process. At the end of heat exchanger cooling, we have the temperature of air 60 degree Celsius, and this one is a 4 to 5, that is a expansion process which take place in turbine. After the turbine, 5 to 6, that is a journey of air from the turbine exit to the cabin. And point number 6, that is a cabin temperature, that is given T6 22 degrees Celsius. Here that is in Kelvin 295. So here everything, all the data already we have listed out here. All these values now we will use one by one. We will follow the steps in the analysis. So first of all, while solving the problem, we use first step, that is a ramming. For the ramming, for ideal ramming, we use temperature ratio formula. Means T2 by T1 temperature ratio during the ramming process, that is equal to pressure ratio, and the exponent is what? Gamma minus 1 upon gamma. So here by putting the values over here, T2 we have to calculate. T1 is given, that is 20 degrees Celsius, means 293 Kelvin. All the values of the temperature we take in Kelvin here in the calculation. Pressure ratio T2 by P1, the values are 0.9 and 0.8. So here the unknown value, that is T2. So when we calculate, we find T2 is equal to value 303 Kelvin. So this is at the end of diffuser exit temperature. Diffuser exit temperature that we obtained. The next step is compression. So for the compression, now here we can take help of the two formulas, because associated with compression process, one formula already in theory we have seen, that is temperature ratio and pressure ratio relation. Another one is efficiency of the compressor. Both formulae we can use, and the known values we will put. So 2 to 3 process, that is a compression. Obviously it is isentropic compression. So for that, first of all, we can use the formula, that is a temperature ratio T3 dash by T2, because here we can see this is a ideal process 2 to 3 dash. So for ideal process, temperature ratio T3 dash divided by T2, that is equal to pressure ratio P3 by P2 at the exponent gamma minus 1 upon gamma. So here from this equation we can calculate. Now this T2 will come on the right side. T2 already now in the last step we got here T2 303. So this value we will use now, 303. P3 value 3.6 bar, that is after compression, and P2 value, that is 0.9 after ramming. So these values we will put, and here for the betterment of calculation you can put the value 1.4 minus 1 divided by 1.4 and you can calculate, and directly you can use that value in memory in the calci, so that you will get values fastly. Calculation will be fastly. So this complete calculation that comes 0.2857. So every time it is required in the numerical, many times we use this part. So that is why value of this part 0.2857. So by doing this calculation, now we find T3 dash that is equal to 450 Kelvin. This is the ideal temperature, ideal compressor exit temperature, ideal compressor exit temperature we have obtained. Now by putting this value, we can get actual compressor exit temperature. So for that we use efficiency of the compressor formula. So compressor efficiency formula we will use here diagram. In the theory I already mentioned that how to find efficiency. So taking the temperature difference ratio, and here efficiency should be less than 1. Means here this is a small difference, means ideal temperature difference, ideal compression temperature difference, temperature rise of ideal compression divided by actual temperature rise. So this formula we can use. So formula ideal difference divided by actual difference, temperature rise difference. Now in this case we are given efficiency of the compressor 0.8. T3 dash we calculated, immediately you can use it. Or T2 is also calculated during the last steps. T3 is to be calculated. So from this calculation we find actual exit temperature of the compressor, that is 486.75 Kelvin. This is what actual compressor exit temperature. So here we have completed the ramming process part and compression process part. Now beyond this, now the part comes that is what, as per the diagram, heat exchanger. Here cooling process in air cooler take place. Cooling in, we call this device as a air cooler. Heat exchanger we call it as air cooler. So 3 to 4 process now we can do the calculation. And further that calculation, when if we don't need, if we know the temperature, because here in this example we are given T4 temperature. If the temperature is not given, in that case in the numerical, effectiveness of the heat exchanger should be given. Now in this example effectiveness of the heat exchanger is not given, but directly temperature 4 after heat exchanger, that is T4 is given. Means here T3, T4 we know. So that is why it is not necessary to go or to use effectiveness calculation step in this numerical. So now we can go directly. Now 3 and 4 we know, so now we can go directly to this calculation. 4 we know, we have to find 5 because 6 is given. 5 we have to find. So this 5 how to find? For that this is the expansion process. For the expansion process we have to use here 2 formulas. One is a temperature drop, because in the turbine expansion process temperature drop take place. So temperature drop ratio, pressure ratio, that relation, and efficiency of the turbine, that formula. So by using these 2 formulae, now we can proceed to the next step. So here that is a process 4-5. That is expansion in a turbine. 4-5 process. So here set of 2 formulas. One is a temperature ratio T5 dash divided by T4 that is equal to P5 by P4 gamma minus 1 upon gamma. This is a formula. Okay, so here we don't know T5 dash. Okay, so that is why we use this formula. See here in the this is a process. So for the expansion process, T5 dash divided by T4. This is a formula, temperature ratio. T5 dash divided by T4. Temperature of 4 point in Kelvin 333. That is given in the given statement. P5 means cabin pressure given, and P4, that is a 3.6 pressure is given. Now this P4 pressure is actually equal to P3 because after the compressor 3.6 bar pressure is given. After the compressor 3.6 bar pressure is given, but the process, cooling process, that is heat rejection in a heat exchanger, that process is constant pressure process. So that is why here pressure of point 3 and 4 both are same. So here P3 is equal to P4, and that is why here in this calculation now value of P4, that is 3.6. This exponent already we discussed about it, how much it is to be taken. Now by this calculation, by doing this calculation, we get the value of T5 dash, that comes 230.94 Kelvin. This is a half calculation of the 4-5 process. Now remaining half process by using the formula of turbine. So turbine formula that we have seen in a theory, that is a actual temperature drop T4 minus T5 divided by ideal temperature drop. Ideal temperature drop. So you can see here for this. Here this is a ideal temperature drop T4 minus T5 dash, and actual temperature drop, that is T4 minus T5 dash. So here turbine efficiency, that is given 75%. So you take it as a 0.75, 333, that is a T4 temperature given. Here we have to calculate T5. T5 dash is already been calculated. So this value we take here. By doing this calculation, we get temperature at the exit of the turbine T5 256.45 Kelvin. This is actual turbine exit temperature. Actual turbine exit temperature. So in this way we obtain the temperature up to 5 point. Now the next part is to find the actual values which are expected in the numerical. So in the numerical, 3 values are asked to calculate. Out of that, first one is a mass flow rate. So to find mass flow rate, now we will use a formula. That formula is what? Q dot L. Q dot L means cooling capacity. So cooling capacity, cooling load, that is Q dot L. How to find? In the theory we have seen product of MCP for air multiplying by cabin process. That process is 5 to 6 process. So here it comes T6 minus T5. This is a formula. In the cabin, you can see here. This is the exit of the turbine, point number 5. Point number 6 is a cabin where the temperature, where the air is leaving. Cabin. So this 6. So during this 5 to 6, amount of heat that is absorbed by the air from the cabin, that is called as cooling load. So this load is calculated how? By using formula MCP delta T across the point 6 and 5. So point 6 and 5. So this is 6 and 5. Now putting the value of mass flow. Now here the calculation is what? Mass flow rate. Mass flow rate we have to calculate. Q dot L we calculated in a kilowatt. This value is in kilowatt. 70.34. This already we have calculated at the start of the numerical. Because here 20 TR. This value is given 20 TR. 20 TR conversion into kilowatt by multiplying it 3.517. So this Q dot L. Mass flow rate is unknown. That we have to calculate. Specific heat for the air, heat carrying capacity of air, that is 1. And T6 minus T5. So cabin temperature 295 in Kelvin, and this T5 that was calculated. So by putting this now from this equation, M dot A is unknown. So this how to calculate? Here we have to do algebraic operation. Mass flow rate of the air that comes 1.82. Unit of it is what? Kg per second. So this is your first answer of the numerical. Now this mass flow rate we can use for the further calculation, that is to find the power of the system. Now to find the power of the system, we need to calculate two work, that is ram work and second compressor work. So we have to write under the power this calculation. Okay, first calculation was this mass flow rate. So first calculation, mass flow rate. Mass flow rate, that is M dot A. This we calculated. Now the next is power. Power of system in kilowatt. Now to calculate this, we need to calculate first of all W dot R, means ram work. Ram work and compressor work. W dot R and W dot C. These both work we have to calculate. So for that ram work means process 1 to 2. So during this process consumption, that is this formula, MCP delta T across process 1 2. So here by putting the values, we get the calculation. W dot R that comes 18.2 kilowatt. W dot R that comes 18.2 kilowatt. Then compressor process take place in a point number 2 and point number 3, between point number 2 and 3. So that is why the formula is M dot A CP A T3 minus T2. This is the formula. So putting the values, all the values which are here. Let us see what is the value of T3 correctly. 486.75 minus T2. So do this, if you do this calculation, we find the compressor work, that is 334.42 kilowatt W dot C. Now the power to drive the system, power required to drive or to run the system, that is called as net work. So we write this as W dot net. That is what summation of RAM work and compressor work. So summation of these two values. This sum comes 334 plus 18.2. It comes 352.62 kilowatt W dot net. So this is the power of the system. To run this system, amount of power required. Now the final part, that is a COP, third answer, part C. COP, it is a ratio of Q dot L to network, that is power. So Q dot L in kilowatt, 70.34 divided by net power, net work we calculated. Taking this ratio, we find the value of COP 0.193. So this is your third answer. Answer 3. So in this way we calculated in this numerical, or we have seen the procedure to find how to find mass flow rate, network and COP of the simple cooling system of aircraft refrigeration system.